So our deal right now is potentiometer. I told you very clearly what is the objective of potentiometer, right? What is the necessity of introducing potentiometer? All my ammeter, all my voltmeters are not ideal. Technically drawing certain amount of current to measure either the current or potential difference. Potentiometer is an arrangement where it do not draw any current. It do not draw any current. The basic circuit of potentiometer contains, this is called the primary circuit with a primary EMF source and some series resistance. So the objective of series, see, sometimes in the place of series resistance, you may use a rheostat also. You already know what is the objective of rheostat. What is the objective of rheostat? Right. రికార్డ్ చేస్తున్నాం క్లాస్ అంత మునుపు లేవు ఎవరికైనా ఉపయోగపడతాయి రికార్డ్ రైట్ సో దిస్ ఈజ్ రియోస్టాట్ సో now basically this is the potentiometer wire. Actually the in real situation of potentiometer is it will be something like a wooden box like this, and I'm just showing only few. I'm just for purpose I'm just showing few. Actually you will have 10 lines each of 1 meter, because physics laboratory is not like a cricket ground. 10 meters, no room will be of 10 meters. Even our the best room, the best hall dimensions, what hardly it will be some 24 feet. 24 feet. Right. So therefore you cannot run 10 meters at a length. So what they will do is, wire is taken like this. It will make again, it will make likewise. You will have parallel lines continuously. So within the 1 meter area, there will be 10 rows. Normally 10 meters length. Normally. Sometimes, depending upon the requirement, they may use even a lesser version also. So that is a wooden board. Basically, a wooden board upon which you will have 10 lines. Each line is 1 meter. Right. That's all about the potentiometer. Now the lower circuit is what we will call, this part is called secondary circuit. Okay. So for example, the basic structuring is, I will take another battery which is called the secondary source, secondary voltage, whatever it is, a resistance box, high resistance box, a galvanometer, very sensitive galvanometer, and a jock. Basically, what is happening is the place where you are placing the jock will change the nature of the circuit like this. It's like some resistance between AJ, remaining resistance like this, and lower side also another side. You are dividing it like a circuit which we already studied earlier, something like this arrange. You're just making it something like this. But depending upon the place where you are managing J, there is a possibility that the potential drop across this is exactly same as the EMF of this cell. I repeat, depending upon the place where you are placing J, because this is a uniform way, don't forget. Accordingly, the drop across this and the drop in this side will become same. Then what happens? The net current in this loop must be zero. The galvanometer shows zero deflection. At the instant when the galvanometer shows zero deflection, this length, remember, this length is measured from A. Even meter bridge also, length L is measured from A. And that length is called balancing length. But remember, care must be taken. Both the side, positive side must be same side. Suppose A is connected to the primary positive, A must be connected to secondary positive. That is the first care. Second care, in the absence of this circuit, the drop across AB alone due to this must be higher than the EMF of this cell. Why? Suppose if you are not agreeing this condition, which means the drop across this is lesser than the drop across this. Even you place the jock here, you won't find a condition that the net EMF is zero and the galvanometer do not show zero deflection as you move from A to B. See, once when the circuit is connected, even in lab also what we will check is the jockey is placed once here. Galvanometer shows one-way deflection. When you place the jockey here, the galvanometer shows other way deflection. If the galvanometer showing different directions in deflection, your circuit is correct. Suppose I place the jockey here, the galvanometer shows a leftward deflection, for example. When I am placing here, still it shows leftward deflection, then either your circuit is wrong or the condition is not achieved. Once when the circuit is closed, what is that you need to do is you need to check touching here versus touching here. By touching here, if it shows a leftward deflection, by touching here, if it shows rightward deflection, yes, there is a possibility somewhere in between where the galvanometer shows zero deflection. At that point is called balancing. Okay. So the working principle of the potentiometer is you will find balancing length. What you will measure here is balancing length. That's all. Saturday you didn't came? Okay. No, you are not there in the morning class. Why? Right. Now, what am I going to do right now? First of all, you said that the galvanometer is not showing any deflection, which means this is totally now isolated. Nowhere linked with this circuit, yes or no. When galvanometer shows zero deflection, this is totally isolated. Right. Whatever the current that was sent by the primary of the potentiometer, the same current is passing through AB because there is no split. If there is a split, what happens? The galvanometer shows a deflection, and that is not the condition I'm speaking about. I'm speaking about the case where the galvanometer shows zero deflection. The galvanometer shows zero deflection implies whatever the current in the primary is exactly the same current that passed through AB. Right. So therefore, E secondary is equal to means you said the drop across this. Okay, bhaiya, but that is I primary into I am assuming that this portion is of resistance R. So what is ES? ES is nothing but the drop across this, the drop across only this portion of the resistance. That is I primary into R. I primary is E primary by RP plus RS into R by N. Didn't get here. Okay, no issues. E primary by R primary plus RS means R primary plus RS, total current, into I want the resistance of this part. I have no idea, but I know for L length, resistance is RP. For small L length, what is the resistance? That resistance RAJ is nothing but what is that? R potentiometer wire by L times small. That's the D. Now, what is that I am measuring now? E secondary. What is that I got? There are certain terms of interest here. Here, there is one term that I need to define. The entire thing, whatever is there in the bracket, I repeat, the entire thing, whatever is there in the bracket is what we will call as potential gradient. Potential drop per unit length. I repeat, whatever there in the bracket is what we will call as potential gradient. So what is the working principle of potentiometer? E secondary is potential gradient times balancing length. So what is the basic principle, working principle? E secondary is potential gradient into balancing length. Potential gradient remains constant so long you don't change this one, and the y. Yes or no? Boys and girls. Potential difference per unit length. Here, current into RP means the drop across this wire, total wire, by the length of the wire. That gives potential drop per unit length. Into small l gives the drop across this portion of the wire. That is what we want. And that is nothing but yes. So the working principle of the potentiometer is E secondary is proportional to L. So now tell me, till here, any student having doubt? Definitely it should be more than yes. If that is not the case, don't use this device. And I told one more important point also, you ignored. No. But once you have done the circuit part, once you are done with the circuit part, you should check, throw the jockey this side as well as throw the jockey this side. We are showing deflections. If we are showing deflections, and ఊరు నుంచి వస్తుంది బయట ఇద్దరు ముగ్గురు ఉంటారు. So the deflections, both the sides. Got a point? So that is also important. Suppose if this is not done, no use. These are the two fundamental conditions of the. One more important point. The sensitivity of the instrument. Anytime when I am speaking about sensitivity means cause, effect. Two things will be there. Cause and effect. Here, ES is the cause. And this drop is the effect. Okay, right. Now, so see, the sensitivity of the instrument, purely depends on potential gradient. Purely depends on potential gradient. So, least is the potential gradient, more sensitive is the instrument. For example, I am working on a potentiometer wire whose potential gradient is 1 volt per centimeter. And I am using another instrument. I am using another instrument whose potential gradient is 0.01 per centimeter, which is more sensitive. 0.01 is as same as you are using the length of the chalk piece using a meter scale. You are using the length of the chalk piece with a vernier calipers. So therefore, a potentiometer is a very sensitive instrument for measuring, a very accurate instrument for measuring both potential difference as well as current. I'll explain how and all that. Next stage. But one thing is very clear. Whenever I am measuring, what is that I am measuring? I am hardly measuring L. So at the end of the day, whatever that I do as a measurement part, I will measure L. I'll measure L. But remember, when I am measuring L, the current through the instrument galvanometer is D. I am measuring something without drawing current. I am measuring the EMF of this without drawing current from that, which is impossible practically with a voltmeter. When you connect voltmeter, there is some deflection in the instrument. Yes, sir. Oh, when will the voltmeter show deflection? When certain current pass through this. It means you are drawing some current from the battery. When you are drawing current from the battery, you are not measuring EMF of the cell. You are measuring potential drop, E minus IR. Any doubt till this point? Right? Next. So basically, potentiometer used for two purposes. The first purpose is to compare EMFs of two cells, and the second purpose is to determine internal resistance of the cell. Let us see how we will work comparison of EMF. Now you see, I am having only modification is a switch type arrangement. I will place only K1. Only K1 is considered in the secondary. I will place only K2. Only E2 is placed in the secondary. That's how I will adjust. I repeat, I will place only K1. E1 is attached in the circuit. I will place only K2. E2 is a don't plus K1 and K2 together. Okay. Now I am placing E1. Then correspondingly some L1 balancing length I will get. I will place only E2. Correspondingly, L2 you will get. Right. Whereas the potential gradient is common. Why? Because this arrangement you are not disturbing. This battery you are not disturbing. Because potential gradient term contains what? EP by RP plus RS into RP by L. Yes or no? You are not disturbing anything in that. In using E1 and E2. So therefore, E1 proportional to L1, E2 proportional to L2. So E1 by E2 is L1 by L2. This is how I compare the EMFs of two different sources. Suppose if E1 is a standard cell, for example, standard cell, Leyland cell, around 1 point, if I'm not mistaken, because very 1.5 volt approx standard. E2 you will get perfect. When E1 is exactly known, E2 you will get more accurate. So likewise, you can compare, you can calibrate the EMF of a unknown cell, etc. like that. By the way, at the end of the day, please remember, without drawing any current from the cell. That is important. You can do the same with voltmeter. Even voltmeter, you will draw certain current. But here in this, you will not draw any current. Right. Next. Only at balancing point. Otherwise, what you will measure in this? Otherwise, what you will measure in this? Why you will go back? Tell me, what you are measuring in this? Balancing length. When balancing length is obtained, galvanometer shows zero deflection. Only then you will measure anything. Right. Now, why you are going? That is why then potentiometer of no use. If you are drawing something, and remember, I told you all the way. Please remember, when I am comparing EMFs also, please remember the positive side of primary cell, the positive side of E1, the positive side of E2 must have the same pulse. You reverse something, you are done. No use. You won't get zero deflection condition by reversing. Similarly, you can find the internal resistance of a cell using potential. You can find the internal resistance of a cell using potential. How? Simple. Now see, all that I am modifying only in the secondary portion, not in the primary portion. I am just introducing potentiometer today. Thereafter, I will extend my discussion on different aspects. Why I am discussing potentiometer is any problems that you already have an idea that you can go with that, right? Determination of internal resistance of a cell. This is my concept in this. See, there are two ways. One, I will open the key first. I will open the key and I will measure the first balancing. That is corresponding to E secondary is potential gradient times L. I will close the key now. The problem is closing this key has nothing to do with galvanometer. But because that you have closed, you are not measuring the EMF of this portion. You are measuring the potential drop across the cell. Because whether the galvanometer shows zero deflection or not, there is some current that pass through in this loop, small loop. Okay. And because of which you are measuring potential difference. And that is equal to potential gradient times L2. Of course, L1 will be greater than L2. Here there is a mistake that should be corrected because this is less. So J2, J1. This is L2. This is L1. Right. The potential difference is potential gradient times L. Now what is happening? E secondary by V. L1 by L2. But already we know in this, E secondary is capital R plus a small r. Potential difference is I capital R. You know this. So therefore, E secondary by V can be replaced as capital R plus small r by capital. Okay. So therefore, ES by V is corresponding to L1 by L2, which is capital R plus small r by capital R. Solving which, you will get the expression for internal resistance. And that internal resistance is small r is equal to capital R into L1 minus L2 by L2. That is basic operation of potential. Remember, whether to determine internal resistance or whether to compare EMFs, I am not using any current. I'm drawing zero current in both occasions to measure. Any doubts? Clear? Right. Now we will switch on to RC circuits. So any doubt in potentiometer till now, whatever I called, just please. So RC circuit. Ask me again, claritatively. Yes, obviously, which is more, EMF or potential drop? E more length, V lesser length. Clear? Right. Even the full notes is available here. Full notes is available here. Uh, uh, I will deal freshly here. You will have the notes. Anything extra, I will discuss. I will post it accordingly. The RC circuits, again, basically two types: growth, decay. We'll first deal with the growth of current, growth of charge. Basically, you have a capacitor of capacitance C, and you have a resistance R. Battery B. Right. EMF E, and this draws. No, no. See, please try to understand. An uncharged capacitor, behaves like a conductor when connected to a battery. As time proceeds, the charge keeps building up. The charge keeps building up. The potential difference keeps increasing. At some point of time, when the potential difference across the plates is same as the EM of the cell, current becomes zero in the circuit. That you already know. When I have handled only capacitor, that time I did not introduce the resistance, and it is only pure capacitor and the battery. In that case, in a flash of seconds, the capacitor gets charged. In a flash of seconds. In this, there will be delay. For full charging, delay doesn't mean hours, not even minutes, not even seconds, few milliseconds. If you increase R, higher values, you increase R, higher values, what happens? Increase R, yes, delay increases. Practically, when I have done in a degree, post graduation, etc., during that time, we use it to the experiment. You can hear the beep sound. When it attains full charge, we use it to set some circuit where that uses beep charge. So that allows us to understand, okay, completely charge. So what is happening here? There is current at some point of time, charge, that is instantaneous charge and current. Remember, we will call AB DC, VA minus VB is plus Q by C. VB minus VC is plus IR. VC minus VA is minus. You apply Kirchhoff law. So you will get the condition E is equal to IR plus Q by C. Any doubt in equation 1? Ask me right now. Any doubt in equation 1? Ask me right now. Are we clear? Any doubt in equation 1? Ask me right now. Okay. How to define current here? That's a problem. Current is defined in this case as dq by dt. Current is defined as eq by dq by dt. Remember, I have used plus symbol here because charge is growing. The positive sign indicates on the plate charge is increased. Now use these two equations. So E minus Q by C is dq by dt times R. So dq by E minus Q by C is dt by R. We have a situation like this. In mathematics, you know, whenever you have a situation like this, with this limit, you will write that as 1 by b log e a plus bx2 by a plus bx1. We know, we already know this. తగ్గిపోయింది ఇది మామూలుగా అంత ఫుల్ స్క్రీన్ వచ్చేది రైట్ రైట్ ఓకే clear any doubt till this point? So I am going to apply this. I know initially there is no charge. I told you uncharged plate. Even that initially charged, what happens also I will discuss, but at a later stage. This is a fundamental discussion. Right now, what I am doing. Today, it is 0th part of the class. 0 at some time t, at some instant q. This is t minus 0, t by r. Q is equal to C. C is the maximum charge that this capacitor can have. Any doubts till this point? I am asking you again. Let this be equation 3. Any doubts in equation 3? Please ask me right now. Any doubts in equation 3? Any doubts? What is your doubt? Yes, obviously. Otherwise, I need to consider the internal resistance also. In the place of capital R, I will write capital R plus small r. In the place of capital R, I will write capital R plus small r. That's all. Otherwise, rest everything is the same. Equation. Yes. Yes. What is RC? Suppose you take capacitor as 1 microfarad, resistor as a 1 farad. RC is how much? 1 microsecond. For that 1 second itself is a very long time. If you plot a graph taking time along x-axis, charge along y-axis, you'll get a graph like this. that steady state charge, that is called steady state charge. At steady state, maybe that happens, t tends to infinite, or dq by dt is equal to 0. That is called steady state. At steady state, the charge is Ce, and this is max. That is the maximum that you can store in that under these conditions. Okay, there is a special time. What is that special time? At the time t is equal to RC. This term RC, wherever it comes, we will call it as some tau. There is a special name for this, which is called time constant, because RC have a dimensions of time and it's a constant. So it is called time constant. So at that t is equal to RC, you know what will happen? The charge becomes, at t is equal to RC, the charge becomes Ce times 1 minus 1 by E. E minus 1 by E, if I am not mistaken, nearly 0.63 approx. 0.63 approx. So at this point, it is 0.63 times C. Any doubts? What about current? That also important. You told that current is dq by dt. dq by dt means differentiate this Ce times 0 plus 1 by RC times T by RC. Whereas this will become E by R times T by tau. E by R is considered as maximum current. In fact, this is the current when T is equal to 0. The moment you close the switch, this is the current. This is e to the power of minus T by tau. Understand as if here, what is happening. X-axis, Y-axis, time, current, boys and girls. That's how the current falls. By a t is equal to 0, the current is I naught. At time t is equal to tau, it will become 1 by E times of the maximum value. 1 by E is 1 by E, 0.37. 0.37 times the maximum current. That's about current. So I have given you two graphs, how the current varies with time, how the charge varies with time on plate. Remember, when I am drawing, charge means, I told you very first itself, for a capacitor, when we are speaking about charge, implies there is a charge on the positive plate. There is the charge on the positive plate. Net charge 0 anyway. The charge on the positive plate is a function of time, is what you have. Any doubt till this point? Any doubt? Zero. Oh no. Yes. Net EMF is decrease. Net EMF to drive the current is decreasing. When the drop across the capacitor plate is same as the EMF of the cell. So at t is equal to infinite, the capacitor behaves like an open circuit. At t is equal to 0, uncharged capacitor behaves as short circuited. It's a conductor. Now, what is happening? I want to just see this. At an instant, across the plates of the capacitor, across the plates of the capacitor, right? I is the current. That instant plus Q is the charge. Now, therefore, what is the power delivered to the capacitor? The power delivered to the capacitor is simply I times Q by C, Q by C times dQ by dt. This is rate of doing work on the capacitor at an instant. And you know clearly both functions. I is E by R times T by tau, 1 by C times 1 by C times there Q by C is nothing but E times 1 minus E to the power of T by tau. Now, you take the same thing, it's E square by R times E power minus T by tau minus 2T by tau. Remember, power changes. Initially, it reaches some maximum value. Thereafter, it again comes to 0. So, where is power delivered across the capacitor maximum? 0. So, you need to differentiate this now. So, it is like minus 1 by tau times e to the power of minus t by tau plus 2 by tau times e to the power of minus 2t by tau is equal to 0. Tau times natural logarithm of 2. At that instant, power delivered across C is maximum. Any doubt till this point? Next. What about resistance? So power delivered across the resistor is I square R. I square means E square by R minus e to the power of minus 2t by tau. In fact, it is a maximum at t is equal to 0. It is a maximum at t is equal to 0. Maximum at t is equal to 0. 0 at t tends to infinity. And there is another observation. At some instant, PR may be equal to PC. Power delivered across capacitor, same as power delivered across the resistor, which means is equal to E square by R T by tau minus 2T by tau. It happens at an instant t. It won't happen all the time. At an instant t. So this means this means this means are interesting. This is the same time when power delivered across the capacitor is maximum. When power delivered across the capacitor is maximum, that is the same instant when power delivered across capacitor and power delivered across the resistor is same. I repeat, at the instant when the power delivered across the capacitor is maximum, the power delivered across the capacitor and power delivered across the resistor is same. That's all. This is about the growth curve. Any doubts till this point? Ask them. Any doubts? Any doubts till this point? Ask them. And one more important point in this, as you know, power delivered across a resistor, okay, is I square R E square by R minus 2T by tau. This is purely for heat. So the total heat delivered is E square by R minus 2T by tau dt. T is equal to 0 to infinite. Yes, please help me in writing this. E square by R constant. Minus tau by 2 constant for integration. And this becomes e to the power of infinite, e to the power of minus infinite, minus e to the power of 0. This will become e square by R tau by 2. Any doubts in this? Yes. That is none of your business. I am working on resistor. Now, why you are asking something else? Remember, when I am working on this, focus on this. I am dealing independently. Only through resistor, what is happening? Right. E square by 2R. Tau means RC. RR cancel. So half of C is square. By the way, what is the work done by battery? C is square. What is the energy stored in capacitor? What is the difference? And the total loss is half C is square and half C is square, total loss. But half C is square is stored in the capacitor only, no? Battery done C is square work, out of which half C is square there is account, which is stored in the capacitor in the form of energy. Rest of C is square is loss in the form of heat. That's what shown. Any doubts? Any doubts? Again, last time. Any doubts till this point? Huh? PR? PR graph? Is the same as like this. Whereas PC graph something like this. It reaches till maximum and thereafter it again falls to 0. This happens at t is equal to RC times natural logarithm of. This is a complete description on growth of charge in a capacitor. Now we will move on to decay of charge in a capacitor. So till this point of time, our discussion is with the growth of charge. It is called growth of charge. Now I am dealing with the decay of the charge. What exactly that means? I already have I already have this is fully charged and at t is equal to 0, q is the charge. Now the moment I close the key, what happens is it will discharge. Now here at an instant, if q is the instantaneous charge on the plates of the capacitor, minus dq by dt is the current through the resistor. Now why there is a minus sign? Why there is a minus sign? Because the charge is decreasing on the plate. And now you apply Kirchhoff law here. Plus IR is q by c. Minus dq by dt times r is q by c. So minus dq by q is dt by rc. Again, you got the same time constant. So therefore, limits. Initially q at an instant q, dq by q. And that is t is equal to 0 at some time t, dt by rc. So this is log e and that is okay, clear? Q is equal to q into e to the power of minus t by rc. Now see, very clear now, I've understood. The charge pattern is like this. And the current pattern, is minus dq by dt. So what you will get? Q by rc e to the power, right or not? Minus t by tau. Remember, q by c is the initial potential drop. Potential drop by resistance. The initial current means current at t is equal to 0. This is the current at t is equal to 0. This is also behaving the same way. And I don't want anything to discuss in this because there is no source. If there is source, there is something to discuss about how the power delivered, what amount of power delivered, etc. Like so, I taught you two things today. Everything is basic. Zero of the chapter. Growth of charge, decay of the charge. But sometimes what will happen in some circuits, you won't see direct RC circuit like you may see some complex circuits. Like for example, I'll just take a direct example. You have a battery whose EMF is 6 volts and resistance 3 ohms, another resistance 3 ohms, capacitor of capacitance 1 microfarad, initially uncharged, and this is 6 ohms. That's how your circuit is. Let us label points A, B. Remember, this is not your regular RC circuit. Normally, what you will do is you will apply Kirchhoff laws and all that. Finally, you will come to arrive about the charge and all that, the current through the capacitor and all that. But it's a lengthy process. You can solve this very simply. How? You need to study 3 stages. At t is equal to 0 circuit, at t tends to infinite circuit, at an instant t circuit. At t is equal to 0, replace the capacitor with, right, this is how the circuit will be. We already know 6 ohm, 3 ohm parallel is 2 ohms, 2 ohms and 3 ohms, 5 ohms. 6 by 5 is 1.2 amps. And that 1.2 again splits here, 1:2 ratio. Okay, 1/3 of 1.2 is 0.4. 0.4 ampere will pass through here, 0.8 ampere will pass through here. I can say the maximum current through capacitor is 0.4 amps. Any doubt? Right. At t is equal to infinite, remove the capacitor. At t is equal to infinite, remove the capacitor. So what is your circuit thereafter? 3 ohm, 3 ohm. So what is the drop across here? 3 volts, which implies the maximum potential drop across capacitor is 3 volt. And at this stage, no current pass through the capacitor. That's called steady state. At steady state, there is no current through the capacitor. Now, what is the maximum charge across the capacitor? Simply CV. I have given 1 microfarad and the drop is 3 volts. So therefore, 1 microfarad into 3 microcoulomb. That's the maximum charge. Left one extreme, right one extreme. In between, remove the battery with the internal resistance. Yeah, fortunately, I have selected a radial battery. This is across the capacitor. So what you have is 3 ohm, 3 ohm, 6 ohm. So across these 2 points, X, Y, what is the effective resistance across X, Y? 3 ohm, 3 ohm parallel 1.5, 1.5 plus 6, 7.5 ohm. You know, the in this circuit, the equivalent time constant. What is that? Equivalent time constant is R. C is 1 microfarad. So therefore, this is 7.5 times second. These are 3 stages. Left extreme, in between, right extreme. So any student having doubt at t is equal to 0 level? Any student having doubt at t is equal to 0 level? Anyone? Similarly, any student having doubt at t is equal to infinite point, steady state? Why you will imagine like that? See, you imagine something, you are not listening to the proper concept. You will extrapolate that in the exam and you will say, I'm conceptually wrong. Did I mention like that? No. Why you are imagining like that? No, no. E is equal to infinite. That thing goes through the capacitor. And the full drop across 3 ohms is the same across capacitor. That's all. Why you are taking again battery and all that? Okay. Okay. No, see, try to please understand, nothing is flowing through the capacitor. So the drop across the capacitor and the drop across the 3 ohm is the same. The net current in that right side loop is D. That is a steady state. An instant, long time after closing the key, you will know. The point is, imagine the world as what I show. You have your own imagination. The problem is when you are reaching half the problem, there exists some confusion. What kind of confusion you will face is whether to go with this or whether you go with that. That's the problem. Next. The next point which I would like to highlight is, okay, fine, everything is good. What about the instantaneous current through the capacitor? Simple. I know what is the maximum current. Where is my maximum current? 0.4 amps e to the power of minus t by tau. Done. I know what is the charge, instantaneous charge across the capacitor. What is that? The instantaneous charge across the capacitor is Q max times 1 minus e to the power of t by tau. Yes, this is a growth case. Hello. What formula we have used in growth case? Q max 1 minus e to the power of minus t by tau. What is maximum charge? 3 microcoulomb 1 minus e to the power of t by tau. So I have given everything. Now you know at an instant what is the current through the capacitor, at an instant what is the drop or what is the charge across the plates of the capacitor. You can find everything from this. We are not comfortable. Good. I am not comfortable with all these things. Good. And what options do you have is take the same thing. paste it now. So now you are closed, right? Now imagine this is main current, this is the IC, this is I minus IC. Apply Kirchhoff. So which means Q by C plus IC into 6 minus I minus IC into 3 is equal to 0. Equation 1. And minus 6 volts plus 3I plus I minus IC into 3 is equal to 0. Equation 2. Plus another big loop. Minus 6 plus 3I plus I had dq by dt. Q by C plus IC into 6 is equal to 0. 3. What are unknowns? I is an unknown, IC is an unknown, right? Q is an unknown. You have 3 equations. Solve the 3 equations. You will get the values for Q, for IC, and as well as for I. That's all. Close this. Ram Karthikeya. Best. This is the best. Go with this. You are done in minutes. You go with this. It's a laborious calculation. You can do in any way. Choice is yours. So what I have done now, the basics. Basics of some RC circuits. That's the point. So gradually, as time proceeds, we will do the next models. Now give me a confirmation on whether you followed these models or the third model. I mean, growth I have taken separately, decay I have separately taken, and this one. Now, yes, yes. Uh, uh, Thevenins type look like Thevenins only, right? Now let us take the first question here. Yes, everyone start working on this, right? एक रहा स्टेम्स ఫిజిక్స్ ఎంత వచ్చాయి సహస్ర వ్యాట్ ఎంత వచ్చాయి నీకు ఎందుకు వచ్చాయి ఆ క్వశ్చన్స్ అన్ని ఎన్ని అసైన్మెంట్ క్వశ్చన్స్ ఉన్నాయి కదా మరి ఎందుకు చేయాల ఏం మేనేజ్మెంట్ ఎంతసేపు చేస్తారు అది ఎందుకు ఇచ్చావు ఎవడమ్మన్నాడు మ్యాథ్స్ సార్ చెప్పాడా అరే 1 అవర్ ఇవ్వాలని చెప్తున్నాను కదా ప్రతి సబ్జెక్ట్కి ఎందుకు ఇలా అందుకే ఈ వీక్ అసైన్మెంట్ లేదేమీ లేదు ఏమేమన్నా ఇచ్చి ఉపయోగం రషీద్ నువ్వు పెట్టావా మార్క్స్ మొన్న టోటల్ ఎంత వచ్చింది ఫిజిక్స్ ఎంత వచ్చాయి వ్యాట్ రామ్ కార్తికేయ పెట్టి నీకురా ఫిజిక్స్ 38 అని చెప్పిందా టోటల్ నీకు వాడరా వ్యాట్ ఏ పడిపోయింది వాడ ఎన్ని క్వశ్చన్స్ మన వ్యాట్ మన అసైన్మెంట్ ప్రాక్టీస్ పార్ట్ నుంచి వచ్చాయి. నీకు కూడా తక్కిన ఎందుకు అసైన్మెంట్స్ నుంచి చాలా క్వశ్చన్స్ వచ్చాయి కదా, ఎందుకు తగ్గాయి? వన్ అవర్ ఏదైనా అంతే కదా. ఎందుకు అయిపోయిందా క్లోజ్ చేస్తా? ఎందుకు చేస్తా? 1 అవర్ కదా మనం ఇవ్వాల్సింది. అది ఏ అవ్వని అయిపోయింది. వ్యాట్ ఎగ్జామ్స్ ఎనీ టైం ఈచ్ సబ్జెక్ట్ ఈ షుడ్ గివ్ 1 అవర్. మ్యాథ్స్ ఈజీ పేపర్ వచ్చింది ఫర్ ఎగ్జాంపుల్ 40, 45, 50 వచ్చింది. అప్పుడు మిగతా 2 సబ్జెక్ట్స్ జస్టిఫై చేస్తావా? ఏం లేదుగా చేస్తావా అన్న, నీకు కట్టంతరా ఫిజిక్స్ అంటే. వ్యాట్ ఎంత వచ్చారు? నో, didn't written exam. How much he scored? Tell me only physics. That's all. ఈ వీక్ డిస్కషన్ అయిపోయింది, మిగతా వాళ్ళకి అడిగేదిలోకి పెట్టేది. రైట్, వాట్ ఎల్స్ కట్టాలా సార్? చేసే పేపర్. I will discuss physics paper tomorrow because I want to start topic today. Why I have done this is I felt majority of the questions are assignment based. No, ideal, unless or until I don't mention it is a. You close, what will happen in steady state? Ignore the path of capacity. Then what happens? 4 plus 6 plus 2, 12 ohms. The current is at steady state. At steady state, the current is 24/12, 2 amps. Means the drop across these 2 points alone. Like for example, you take temporarily, this is 0, for example. Then 10 ohms into 2, 20 volt. Means this is 20 volt. This is you take this as 0 because that part is positive side, 20. So now 2:1 ratio resistances, 4 and 6, 2:3 ratio actually. So therefore the drop is 3/5 times of the total drop. 3/5 times of 20, 12 volt. Correct? This is 12 volt and this is 8 volt. But what about this? Capacitors are in the ratio. Capacitors are in the ratio 1:1/3 or 1:3. Capacitors 1:3. Potential drop 3:1. So 3/4 times 3:1 kada. So 1/4 times of 20 is 5. Across this drop is 5 volt. Across this drop is 15 volt. Clearly, Vx is 15 volt with respect to 0. Vy is 8 volt with respect to 0. Vx minus Vy is 15 minus 8, 7. That's the first part of the question. Right. Next. Find the current to the key immediately when it is closed. Immediately when it is closed, what happens? Entire 4 ohm, 6 ohm track is out of order. The entire thing goes through capacitor. Only 2 ohms is there in the circuit. So therefore, what is the current? For option second question, the current is simply 24 by 2, 12 amps. Find the steady state current, 2 amps. 2 amps, 12 amps. Find the time constant of the circuit. Oh, for the time constant of the circuit, you should redraw the circuit properly. One single capacitor, one single resistor. So across this, what is the effective resistance across those 2 points? By a 10 and 2 are in parallel. So effective resistance is 10 into 2 by 12, 6, 5 by 3 ohms. Yes, this is a 2 ohm, this is a 10 ohm. So across these 2 points, what is the effective resistance? 1. Capacitor or resistance? Capacitance is, C effective is 1 microfarad. Right. So therefore, the time constant is 5 by 3 microseconds. Any doubt? How? Ask me here. This problem arises because you didn't heard that proper. No, you didn't heard that properly. No, you are somewhere else. Why I am checking every time 2 to 3 times after closing up the topic? Because of this reason. Any doubt on this? I am asking again. Time constant. How many are confident? Raise your hand. Right. How many are not confident? Raise your hand. What is your problem? అని ఇందాక చేసినప్పుడు ఏం చేశాను ఇప్పుడు నేను డిస్కస్ చేశా కదా అప్పుడు ఎందుకు అడగలా నేను 3 టైమ్స్ అడిగాను కదా అందుకు సజెస్ట్ చేసేది నేను ఒక క్వశ్చనే అవుతుంది నాకు 15-20 minutes. So I told you very clearly how to find time constant. The technique is now make this totally single capacitor. You have that single capacitor here available. That's the single capacitor. This is entire thing 10 ohms. Across these 2 points, what is the effective resistance? That's what I have done here. When I am finding effective resistance, that's what I have done here. So then what is the path? This is 1 plus 6 ohms. The same thing. Across this 10 ohms, 2 ohms, parallel. Right. 10 into 2 by 12. 10 by 6. 5 by 3 ohms. C effective 1 microfarad. Already you told me that. Because 4 by 3 microfarad, 4 microfarad series combination. 3 by 4 plus 1 by 4 is 4 by 4, 1 microfarad. 1 by C is equal. 1 by C is 1 by C1 plus 1 by C2. 3 by 4 plus 1 by 4. 4 by 4, 1. Right. That's all. Find the current through Y as a function of time. Same what I told you is, now you want a current. Good. Simple. Now, what is the current through the capacitor? That's what you need to find all the time. Because the current will split undoubtedly. Some part across IC, some part across. Here, this is 24 volts and 2 ohm, 10 ohm, 1 microfarad capacitor. So this one will deliver I current, I, IC, I minus IC. So in the loop, Q by 1 microfarad minus I minus IC into 10 is equal to 0. And you take a bigger path, this one, minus 24, okay, plus 2I plus I minus IC times 10 is equal to 0. What are the unknowns here? I is an unknown, IC is an unknown, Q is an unknown. Okay. So what is a Q? Q is nothing but dq by dt is IC. So you have three equations. Solve these three equations. This is a traditional way. The other method which I suggested you is actually useful here. So now T is equal to 0, maximum T is equal to 0, the maximum current through the capacitors is 12 amps. T tends to infinite, steady state. The drop across the capacitor is 20 volt. Okay. So the maximum charge is 20 microcoulomb. At any instant, the charge is 20 times 1 minus e to the power of minus t by tau. Already you know equivalent tau. You got Q. Differentiate that, you'll get in 2 steps you will get. Okay. Choice is yours. Whether you go with equations or whether you go with this technique, it's purely your choice. Any doubt? Any doubt on this part? Everyone in the class. Too early to pick that question. Yes. Work on this. This is the last question which I am discussing today. Current through the battery in the circuit shown in the figure. RC circuit. Okay. Right. What is the current through the battery in the circuit shown in the figure immediately after closing the switch? Immediately after closing the switch, the path is, that's the path. Anyone having doubt on this, please raise your hands right now. Immediately after closing the switch, that's the path. Any doubt? Anyone in the class? Anyone in the class? Right. So, and that current is going to be E by R. So, when one is correct, two is wrong. After a long time, what will happen is that you avoid all capacitors path. The path is, even in that case, it is E by 2R. This is now. You cannot question about equivalent time constant in such circuits. They are badly scattered capacity. You cannot question equivalent time constant like kind of thing in these circuits. Because to ask that, entire capacitor must be in one branch. But it is not like that. Scattered across. Okay? Right. So that's all. I'll just close the class here at this point. An introduction only.